Hi everyone, I'm Apurva Virkud, and I'm excited today to share some work that I did with my collaborators at Illinois. We investigate how endpoint detection uses the MITRE ATT&CK framework. So finding metrics to evaluate security systems has been a historically challenging problem. And one domain where this has recently manifested is in evaluating endpoint detection and other intrusion detection systems. MITRE ATT&CK was introduced in 2013, and since then companies have jumped to use coverage of this metric coverage of this framework as a metric by which to evaluate and advertise their systems. And we can see several such advertisements on the slide. Let's take CrowdStrike, for example, a notorious endpoint detection product. Here, they advertise 99% detection coverage in the MITRE ATT&CK evaluations. And 99% detection coverage sounds pretty good, but what does this actually mean? Does it correspond to detecting 99% of all attacks a customer is likely to experience? Or is it detecting 99% of previously cataloged system log behaviors? So there's a risk for misinterpretation with the attack coverage metric, like conflating 99% coverage with 99% secure. And more importantly, the prevalence of attack coverage in marketing and evaluation materials raises a question. Should customers rely on attack coverage to choose a security system for their enterprise? In this paper, we want to understand how MITRE ATT&CK is integrated into real-world endpoint detection systems. Then investigate, is attack coverage a suitable metric to evaluate them? So let's zoom out. What is MITRE ATT&CK? ATT&CK lays out a taxonomy of adversarial behaviors. And the top level of this taxonomy is tactics, and these are the attacker's high-level goals. There are 14 unique tactics, which are laid out here in approximately chronological order as they would occur during an attack. Early on, the attacker would have goals like reconnaissance and resource development, where they try to learn information about their victim enterprise. As the attack progresses, we have tactics like privilege escalation and lateral movement, where the attacker may try to gain root access on a machine and eventually move through the network. The attack may conclude with goals like exfiltration and impact, where the attacker aims to steal data and interfere with enterprise operations. The tactics can be broken down further into techniques, which are adversarial actions. So take the tactic of privilege escalation, for example, that has 14 associated techniques. The last layer is procedures, which are observed implementations of techniques. So as an example of this entire hierarchy, the high-level tactic of privilege escalation can be accomplished via the technique access token manipulation. And then at a procedural level, this technique has been observed to be utilized by malwares like Appleseed, Black Cat, and Sunspot. Now let's look at how this framework has been integrated into endpoint detection. In this work, we focus on rule-based endpoint detection because this is a widely deployed system in enterprises today. This slide shows rules from 3 popular systems, Carbon Black, Splunk, and Elastic. So in the middle of this slide, we can see the rule syntax, which encodes the conditions in the system logs that we're looking for. And then on the right, we have the vendor-tagged MITRE ATT&CK techniques and tactics. As an example, let's take this Carbon Black rule. It's looking for a Windows event utility process that can be used to destroy system logs. So they've tagged that with the technique indicator removal, which corresponds to the tactic of defense evasion. Note that rules exist on the procedural level of the MITRE ATT&CK framework. They capture a specific implementation of the broader technique. This leads to a sort of disconnect. When a vendor says they have 90% coverage of the MITRE ATT&CK framework, what they're actually saying is that they have a threat detection rule for 90% of the techniques. And remember that threat detection rules exist on the level of procedures. So technique coverage doesn't actually tell us about how many procedural level threats that we can detect, how many real-world malwares that we can detect. It's possible that technique coverage is too high level of a metric to be meaningful. So to investigate, we need to see how this integration of MITRE ATT&CK plays out in real-world settings. So in this work, we analyzed 3 widely popular commercial products, Carbon Black, Splunk, and Elastic. You can check out our paper for results on an additional crowdsourced system, Sigma. So all of these systems have hundreds of rules that are tagged with MITRE ATT&CK techniques. And in addition, each rule is also tagged with some other metadata, things like the description of the captured behavior and quantitative metrics like confidence, risk, and severity. And this metadata can help contextualize alerts for security analysts. For our first research question, we are interested in high-level statistics about how products tag rules with attack. And so in this figure, we look at the technique coverage under each tactic. The y-axis corresponds to the 14 tactics organized here in chronological order, approximately, on the left-hand side. For each tactic, we have 3 bars, 1 per product, that shows the number of unique techniques covered under that tactic. Now, the green dots show the total number of techniques defined by MITRE. So the gap shows the number of techniques that are not covered under that tactic. So our first observation is that for each tactic, the bars across products are fairly similar. So that means that products tend to prioritize the same tactics. Tactics like reconnaissance and resource development that occur at the beginning stages of an attack are much less covered than tactics like persistence and privilege escalation. And in the paper, we also have an additional analysis that shows that products also tend to prioritize the same techniques. We also calculate the union of techniques across products and determine the combined technique coverage under each tactic, shown by the overlaid bars. We find that even when combined, the total coverage is far from 100%. So what this means is even if an enterprise chose to deploy multiple endpoint detection products, they still won't be able to achieve full coverage of the attack framework. We also want to investigate the impact of risk, severity, and confidence on coverage. So these three metrics can be used as somewhat of a proxy for operational value. Security analysts are more likely to prioritize alerts from rules with higher values. And at a baseline, we note that all of these products hover around 50% coverage of the attack techniques. Now focusing on Splunk, which has a baseline coverage of 52%. When we filter out low-risk rules, the coverage drops to 43%. And if we filter out both low and medium-risk rules, the coverage is halved to only 25%. So we see that technique coverage is inflated by the presence of rules that may be of lower operational value to an enterprise. We just saw that products do not cover all of attack, even when we combine their rules. So for our next research question, we investigate why that is, why certain parts of attack are not covered. To do this, we conduct a qualitative analysis of the unimplemented techniques. 3 coders analyzed the 53 techniques that are not implemented in any of these 3 commercial products. And overall, we find that many techniques are difficult, if not impossible, to implement as effective detection rules. And the full list of codes that we found are shown in the right table, and you can check out the paper for a full explanation of all of them. For the purposes of this talk, I will go into the top reasons for not implementing techniques. The most common explanation is that the suggested detection methods for a technique are just ineffective. And in some cases, MITRE explicitly mentions that the behavior is difficult to detect. In other cases, detections may lead to high false positive rates when deployed. The second class of techniques are those that target non-host infrastructure, and these are typically outside the scope of endpoint detection products. We also observe client-specific techniques that require knowledge of a customer's environment or deployed services, and we assume that vendors leave these for the customers to implement themselves. Lastly, we want to investigate how consistent products are in applying attack. If 2 products have similar rules, are they labeling them with the same attack techniques? To this end, we first identify rules that are created to address a common malicious entity, things like CVEs, malwares, and threat campaigns. We identify 9 common malicious entities that appear in all 3 products, and they're seen in the Venn diagram on the left-hand side. The Venn diagram visualizes the overlaps in technique annotations between the products for the 9 threats. Notably, I'll highlight Fin7, where we have 3 discrete sets of techniques. There are no overlaps between any of the 3 products. And here we see that even though the products are trying to detect the same threat, they're not using the same attack techniques to describe it. Now, on its own, this might not be a concern because a threat can have a broad range of behaviors. So we investigate a few case studies to understand why this might be happening. First, we look at 2 rules that are associated with the meter printer software. And generically, these rules are both trying to identify named pipe impersonation. The 2 implementations are so similar that the system log event, highlighted in blue, would cause both these rules to fire. And in fact, there's a large group of log events that would trigger both rules. Elastic has tagged this with the technique access token manipulation, while Splunk has chosen command and scripting interpreter and create or modify system process. And actually, both of these vendors have made sensible decisions because named pipe impersonation might involve any of these behaviors. So the key point here is that ambiguity and overlap between techniques at the procedural level is leading to the disagreement in annotation. Next, we look at a case of higher level disagreement, a disagreement in the tactics that are assigned. We look at 2 rules that are aiming to detect potentially malicious DNS activity with the NS lookup tool, and that's been associated with threats like Fin7 and Sunburst. And again, these rules are nearly identical. We observed the event in blue, which is a DNS lookup for the A records of usenix.org. It would cause both these rules to fire. Looking at the tactic annotations, Elastic has tagged this with command and control, while Splunk has tagged it with exfiltration. The consequence of that is that security analysts would be looking at the same system log activity and attribute it to potentially completely different motivations depending on which product they're using. And that has implications for attack investigation and reconstruction. So to sum up, we find that products prioritize similar tactics and techniques, but do not reach full technique coverage of attack even when rules from multiple products are combined. and that's because a fraction of techniques are inherently difficult to detect. Further, products disagree on attack techniques for similar rules due to ambiguities and overlaps within attack itself, and all of these findings call into question the use of attack technique coverage as a security metric. We also discussed our findings with stakeholders in this area. So we spoke to one of the vendors in our study, and they were aware of the tension between attack coverage metrics and effective detections. They are incentivized to increase their attack coverage, although that might not accurately reflect their product performance. We also spoke with MITRE, who confirmed the importance of investigating the details of these low-level detection behaviors. And in fact, they recommended against using technique coverage as an evaluation metric, supporting our findings. Lastly, we spoke to practitioners from a cyber risk assessment company, and they highlighted that the security community is not necessarily aligned about how tactics and techniques happen at an endpoint. So what's next? We have a few recommendations. First, for MITRE, we hope that they can provide more extensive guidelines on how to interpret attack, formalize these relationships between overlapping or connected attack techniques. I'd also like to highlight some ongoing efforts by MITRE. So for the first time this year, their annual attack evaluations will include false positive rates when evaluating rules. And they also have another effort called Summiting the Pyramid, and that team is developing a metric to assess the robustness of individual rules. In that same vein, for practitioners, we recommend taking steps to support other methods of rule evaluation, systematize exchange of rule performance information across organizations, like false positive information, develop alternate heuristics to evaluate rules independent of the environment they're running in. And we hope that all of these efforts can create a more accurate way to measure endpoint detection products. We've also released an artifact for this paper, which includes all the code, and we received all the badges in the artifact evaluation. So you can find that and the full paper at my website at the QR code. So thank you for listening, and I'm happy to take any questions.